So thank you for the introduction and thank you for having me here in general. My name is Guillermo Lugilde. I am a PhD student from the University of Oviedo in Spain. And I'm going to tell you about our newest studies on phase estimation problems, which is one of the most useful applications of quantum computing. And we have just come out with a new phase estimation method, which is quite promising, actually. So it is based on functional quantum abstract detecting systems, also known as functional QADS. So the first question to be answered is, what are QADS, right? Sorry, I'm getting this full screen. Okay, there you go. So QADS generalize those circuits that are able to detect whether there exists a marked element in a given set, just the existence. And so the point is that when we are given a Boolean function, a QADS will output an initial state and a unitary transformation, which we call the detecting operator, that fixes the initial state when the function is equal to 0, which means that there are no marked elements. So any outcome at the end different from C sub 0 would inevitably mean that there are indeed marked elements. These are some examples of QADS. And as you can see, the original purpose of QADS was solving a detecting problem. However, some families of QADS were studied later, and they showed other practical opportunities. I'm talking about combinatorial QADS. They are based on a previous QADS whose detecting operators applications are controlled by m qubits. This configuration was really useful for some eigenvector related problems, the most important of them being the phase estimation problem. So we are going to discuss all of them in a couple of minutes. The answer that we tried to, the question that we tried to answer in this paper was, what if we don't always apply U sub f once every time, but we allow the circuit to apply it more times according to a given or a certain function g. These are functional QADS. The size of a functional QADS is also defined as just the number of times that U sub f is applied. And the question is, will they outperform combinatorial QADS for phase estimation methods? A spoiler, yes, they will, but with a completely different approach. So let me introduce our three protagonists. First one, combinatorial QADS. Okay, we already know that's for g of n equal to 1. And now the two candidates to dethrone it. Linear QADS for g of n equal n plus 1. So the powers would be 1, 2, 3, 4, 5, and so on. And geometric QADS for g of n equal to 2 to the power of n. These ones are going to be the most successful. But before getting into business, we cannot ignore the fact that functional QADS have a very interesting theoretical behavior. For example, depending on the QADS they are based on, they will have a delta detecting time, which was a key feature for QADS in order to apply their main detection scheme, which, let's not forget, that was the original purpose of QADS. But the most interesting one is the fact that the quantum Fourier transformation gate can be reinterpreted as a product of geometric QADS. Let me show you how. This is the QFT circuit. And as you can see, these sub-circuits can be seen as geometric QADS with a decreasing number of qubits, and the Hadamard gates cancel out perfectly. See? So that only an extra column of Hadamard gates would be needed at the beginning. So it's quite an interesting connection here. But fine, theoretical properties aside, let's begin our journey to a phase estimation method. This is our goal. Given a unitary matrix U and an eigenvector whose eigenvalue has a phase, an unknown phase beta, find a confidence interval for beta. So not just an estimation, but a confidence interval. This is the goal. And this is the journey. We will start with a simple decision algorithm, and based on it, we are going to build 3 phase estimation methods: the dichotomy search, the Hadamard test. These 2 were already studied for combinatorial quads. And the third one is the new one, delta approximation algorithm. So here we go. Decision algorithm. We try to decide whether beta is equal to a given angle alpha or not. How do we solve this? We apply a functional quads for a certain, well, for this matrix V, so that if beta equals alpha, then V will counteract, use eigenvalue on C sub 0, and we will always obtain C sub 0 at the end. That's it. But since every algorithm is going to be based on this one, it is worth studying it further. So here you have the probability of a positive outcome in this algorithm. That means the probability of declaring that beta is equal to alpha. We call this the DA formula, and it depends on the number of qubits that you decided to use, the functional quads, and the distance between alpha and the actual beta. If we plot this function for the 3 known functional quads, we obtain this graph, depending on the distance between alpha and beta. So clearly, geometric quads are the best of these 3, but the question is, are they better than any other functional quads? And what does being better even mean? Because as you can notice, the probability is not always lower than the linear one. So the best way of comparing them is by looking at the area below the function, that is the integral. We say a functional quads is optimal for the decision algorithm if its function g minimizes this integral. Here we are fixing a certain number of qubits. And the definitive result: geometric quads are not only optimal for the decision algorithm, but they achieve the optimality with the lowest possible size. So they minimize the integral and the size too. It is now completely justified to base every algorithm on geometric quads when possible, right? So we are ready to take a look at the first 2 phase estimation methods. The dichotomy search assumes that beta belongs to the interval 0 pi, and we run the decision algorithm multiple times for alpha equals 0 and alpha equals pi in order to estimate the value of the DA formula by taking the proportion of positive outcomes. If we obtain a higher estimation on 0, we assume that beta is closer to that endpoint, and therefore it will belong to the interval 0 pi divided by 2. We can keep this process going as many times as desired, and we will obtain an interval as short as desired. That's it. Second phase estimation algorithm, the M-Hadamard test. It is a generalization of the Hadamard test for an arbitrary number of qubits. This is actually exclusive for combinatorial quads because they are the only ones whose DA formula is invertible. It is like this. So the idea is similar. Again, we approximate this value by running the decision algorithm multiple times and taking the proportion of positive outcomes, and we can easily turn that into an estimation of beta itself. Then we can calculate a confidence interval, a regular confidence interval with the student's t distribution for a certain level of confidence A. So these 2 algorithms were already studied for combinatorial quads, and they are the ones to beat. Now let's come up with a new one. The only middle step remaining is solving this little decision problem for intervals. So now we have to check if beta belongs to this given interval of this form. Okay, the way we approach this is by calculating P sub delta, which is simply the DA formula substituted in delta, And again, approximating P sub alpha, which is the DA formula substituted in beta minus alpha. If P sub alpha is greater than P sub delta, that is because this distance is lower than delta, and hence beta belongs to the interval. The problem is this. It is inevitable to have a probability of error of exactly 50% when the distance between beta and alpha is exactly delta. But there is a way of correcting this. We are going to upgrade this algorithm to obtain the interval correction algorithm. So now we not only try to decide if beta belongs to the interval, but we allow ourselves to modify or correct the interval when needed. For example, if we find out that beta is really close to this alpha plus delta endpoint, we can slide the interval towards the right to obtain the interval alpha, alpha plus 2 times delta, which has the same length than the previous one, but a much greater probability of containing beta. This subtle adjustment is actually really cheap in terms of efficiency. I'm talking about just a couple of extra iterations of the decision algorithm. And yet, here you have the result. It improves the accuracy drastically. I mean, this is the before, and this is the after for geometric quads. So, okay, it's an obvious improvement. And we are going to use this algorithm right now. The time has come. Delta approximation algorithm, the brand new phase estimation algorithm. We are given a tolerance delta, and we have to find an interval of this form containing beta for a certain alpha that we now have to find by ourselves. So this algorithm has 2 steps. First step, finding an initial alpha sub 0, which is simply an approximation of beta. We already know how to approximate beta with the Hadamard test. The difference now is that we don't need a super accurate approximation of beta. We just need to get a little bit close. So we are not going to invest too many operations here. And once we have alpha sub 0, an initial tolerance delta sub 0 is chosen, which is going to be much greater than delta. And we apply the interval correction algorithm for the interval alpha sub 0 minus delta sub 0, alpha sub 0 plus delta sub 0. If the outcome is negative, doesn't matter, we continue checking surrounding intervals because we know that beta is not far away until we obtain a positive outcome in one of them. Or maybe the interval is corrected by the algorithm. That's fine too. The point is that now we know that beta belongs to this interval, and therefore we decrease the tolerance, dividing it by a certain factor, and repeat the process until we reach the actual delta and we find an interval of the desired length. When based on geometric quads, this algorithm clearly outperforms the other 2. So here you have the comparison for 1,000 experiments, 1,000 confidence intervals, and for approximately 18,000 operations. Apparently, not enough operations for the dichotomy search, which fails almost 20% of the time. So it's clearly the worst of these 3. The Hadamard test is much better. We fixed a level of confidence of 0.05. That's why it fails more or less 5% of the intervals. But the average length of the intervals is almost 0.03. Whereas for the delta approximation algorithm, first of all, it has almost perfect accuracy. It was perfect in this case. It's not always perfect, of course. Plus the average length, in this case, it was always 0.02 because that is fixed at the beginning. And it only invests around 1% more operations than the Hadamard test. So the improvement is remarkable, I would say. In summary, functional quads generalize combinatorial quads they have a satisfactory theoretical behavior, including a very interesting connection to the QFT circuit. And of course, they provide a phase estimation method, which is far better than the ones studied until now. Of course, the delta approximation algorithm is not perfect. It is subject to new modifications and improvements, so it deserves a more thorough study, as well as functional quads themselves. They also deserve a more thorough study. So our intention is to consider other variations, for example, substituting those columns of Hadamard gates by maybe other rotations like the QFT rotation. And then we can include in the definition other circuits like the quantum phase estimation method, and therefore compare it with the other phase estimation methods more comfortably. So that would conclude my talk. Thank you for your attention. I hope you found it interesting, and I would be delighted to answer any questions that you might have. Thank you very much.
Thank you very much for very nice talk. So we have a question at the chat. In the chat, so we have, I will read this question. Did you also use classical, scholastic, or quantum optimization algorithm to find this parameter beta? If you tried, was there any difference between the method you suggest and the optimization algorithm results?
We didn't use a quantum optimization algorithm because we tried to focus on functional quads. So we only compared functional quads between each other, like combinatorial quads, linear quads, and geometric quads. Since this algorithm is quite promising, our intention is to make a deeper study in future works, because this article was already long enough. So that would be a great idea for a new comparison in a new article, but by now this is what we have, and it's fine. But thank you for the suggestion.
Thank you. We have also a great presentation. So
thank you.
Thank you.